The topic of this video is on function symmetry. And so there are technically 4 types of symmetry that we can talk about when it comes to a function. We can talk about y-axis symmetry, which you see here, which we'll come back to. We can talk about origin symmetry, x-axis symmetry, or no symmetry at all. So those are the 4 big ideas, and they really do go back to what you talked about in geometry when you're talking about shapes. So if you think about y-axis symmetry, essentially, just to remind you that the y-axis is this line. That's terrible tracing. This line right here. Okay, so something that has y-axis symmetry, and they could all look different, but essentially could look like its most basic example of a quadratic, something like a parabola, right? And essentially it means that they are mirror images on the left and right. Mirror images of each other. Okay, so if you were to fold this right side over to the left, it would sit right on top of itself. So one function example of this could be the function x to the 4th plus 15x squared plus 54. And I did go ahead and graph that into Desmos. Let me turn this one off. And that's this one right here. And you can see it actually looks like a quadratic. And something to note is this table right here. So I'm going to transfer this back over into notes so we can kind of manipulate it a little bit or dissect it. But essentially, if you look at the coordinates, what you'll notice is that there's a mirror image of itself in the table, right? And you should see that around that y-axis. So 170 and to 130. So you see this mirror image here, and you also see the mirror image in the next two here, okay? One thing that I think is pretty positive here is that if you thought about this in terms of a general sense, a negative x gave you the y and a positive x gave you the same y. So essentially it didn't matter if x was positive or negative, it gave you the same y. Well, this leads to the algebraic proof of that. Okay, so we could say that we could algebraically prove that this has y-axis symmetry if we plug in this negative x, this negative x right here into these x values, because it shouldn't make any difference. So let's give that a try. So if we were to take out x and put in negative x, so negative x to the 4th plus 15 times negative x squared, if we were to do that, we get the same result, we get the original equation, then we would say that this has y-axis symmetry. So again, when you think about a negative x to the 4th power, that's like 4 negative x's. Well, 2 negatives make a positive, and x times x is x squared. 2 negatives make a positive and x squared, and a positive x squared times a positive x squared is x to the 4th. So plus, there's that x squared, which is just, that part is just half of this right here, so that's another positive x squared, right? So plus 15x squared plus 54, and hopefully what you notice is that the original function, this right here, and the function after I plugged in a negative x, they are identical. So this would say this is a proof. I just proved that they're the same. And once you do that, that then proves that it's a certain type of function. So not only does this have y-axis symmetry, but it is also known as an even, put that n closer, an even function. Okay, so this has y-axis symmetry. It performs, or it satisfies the proof, and therefore is an even function. Even function. Okay, so let's take a look at the next type of symmetry. So origin symmetry is rotation symmetry. Okay, this means to rotate or spin. That's another way for origin symmetry. So your graph might look something, sorry, I have to give myself some guidelines or it won't look anywhere close. It might look something like this. And essentially, if I take this half of the graph and I spin it, if I spin this 180 degrees, it will sit on top. Okay, but you have to spin the whole thing 180 degrees. So it's rotated around the origin. That's how you know something has origin symmetry. So again, I graphed, I took into the account y equals x cubed minus 3x, and I decided to graph that. So let me turn this one off and turn this one on. And you can see from this graph that there's that idea of origin symmetry, that rotation, okay? Taking into account the table, if we were to map this table, -2, -1, 0, 1, 2, what you'll notice is, sorry, I forget which one's first, -2. So -2, 2, 0, and then what you'll notice here, again, if we were to write these two values, which kind of mirror themselves, but they're on the different sides, if we were to write those out, we would have a -x and a -y, and the same function produces a +x and a +y. So like these are both in the same function, they come from the same thing, but we produce both types. So when that happens, we have to account for that. So how we would do that is, one method could be that we actually are going to plug in a -x and a -y and see if we get the exact same thing back. That's the algebraic proof. So instead of just plugging in a -x, we're going to make both negative. So in this case, I would have a -y equals, and then -x to the third power minus 3 times a -x. When we have three negative x's, -x times a -x times a -x, these two will partner up and make a +x squared. But we'll still be left with a -x. So this is going to end up being -x cubed. And when we multiply two negatives, we get a positive plus 3x. And that equals -y. But we're trying to see if we can map this to the original. We're trying to see, can we get this back up to here? And so I want to make sure that I figure out what is y equal to when it is positive. So I'm going to divide everything by -1, which all that really does is change signs. So I get y equals x cubed minus 3x, which in turn is identical. So you would say that the proof would be that when x and y, when we switch both x and y, so when we plug in -x and -y and return to the same function, this then supplies the proof that this is known as an odd function. So it has origin symmetry, it spins, and it's known as an odd function, something that, which makes sense. Remember, odd functions, this reminds me of, x or x cubed or x to the fifth. Those are odd value functions where they start down here and end up here, okay? And the one up here, remember that this satisfies, is known as even if it satisfies or fulfills the plugging in the -x and getting the original function. All right, there are two types of symmetry left. X-axis symmetry is the next. This one is complicated because x-axis symmetry means that this technically isn't a function. So you're looking at something like this. This would be something that is symmetrical across the x-axis, because remember the x-axis runs this way. So to be a function, you have to pass the vertical line test, and this breaks it, because the vertical line test states that if I draw a vertical line and I cross the graph twice, that is not a function. It has two outputs for that one input, and this is an example of that. So the thing that you need to remember that we can kind of skip right to in here is that this is not a function. So a lot of times we label this as neither, meaning it's not odd and it's not even. It's neither of those, okay? There is a table and there are some qualities to this that are still important to relate. So let's take into account the graph x equals y squared minus 2. If we look at this table, we wouldn't give ourselves x values anymore, we would give ourselves y values. So let's say I have the y values -2, -1, 0, 1, 2. If you plug those values into the equation, that will lead you to your table value. So you're kind of thinking backwards here. So you end up with 2, -1, -2, -1, 2. So what you notice again is that you get the same x value when y is negative as you do when y is positive. So what we're changing this time, what we're looking at is, this is something that has x-axis symmetry. If when we plug in y, positive and negative, we get the same x result. So think about this. Will I get question mark x if I plug in a negative y to that point? And in this case, we absolutely will, because remember that negative y times the negative y is just y squared, which is exactly where we were when we started. Okay, well, I guess it's up here, sorry. So this checks out. This is the algebraic proof. So we are plugging in a negative y to get back to the original. Remember, that doesn't lead to a type of function because this does not pass the function test. There's also this last group. It has no symmetry, so it's not, so essentially, and the graph I'm not even going to show because there's so many. So it doesn't have, there's no x-axis symmetry, there's no y-axis symmetry, and no origin symmetry. They still say neither for this, which is weird since there are 3 options, but here nor there. So this has neither symmetry, none, no symmetry, and that means it's a neither in terms of the function too. So meaning it's not even and it's not odd. So if you graph it and you realize, wow, that doesn't have any type of symmetry, it has no symmetry and it has no even odd qualities. And this would also mean that there's no algebraic proof, because what ends up happening is when you show this, you don't get the same result. You know, you plug in something and it doesn't result in the same thing. This is going to give you an example of that. Okay, so everything just kind of is broken and doesn't work. All right, so the example, I think I have one of a neither. Maybe I don't. This would be an example of neither right here. Okay, so when you do this, if you were to plug in if we look at this, you can see this clearly has no symmetry, right? There's no way to flip this from left to right, top to bottom, or rotate it, because we have to rotate around the origin, and that won't result in the same function. And if you think about this, if our function was x cubed plus 27, if you think about this further, if you were to equals y, sorry, if I were to plug in a negative x, I'm not going to get the same thing back. I'm going to get y equals a negative x cubed plus 27, which is not the same, right? That doesn't work. So I'm going to change that color, sorry. So this breaks it wrong, right? If I were to plug in a negative y and a negative x, the problem is that I would get a negative y equals negative x cubed plus 27, and when I go to get y by itself, I get y equals x cubed minus 27, which again is not what we were given. Okay, so that doesn't work. And if I plug in a negative y, it just flips the signs again, and I get back to the same thing. So there's just lots of things that are wrong here. So this is a neither it's not symmetrical, it's not even or odd, and you would just write neither for both. So on the bottom here, what I'd like you to do is to go ahead and try to see if you can identify. So what I'd like you to do is to graph the equation and then determine what type of symmetry. So remember, this is even, I'm sorry, I take that back. So sorry, wrong blank there. This is either y-axis, x-axis, or origin, or none. Your proof if you need to show one. And then this is either even, odd, or neither. So that's what I'd like you to try, okay? I'm gonna go ahead and fill in the answers here for you just so you have something to check back to. And if at any point I lost you, you are struggling to figure this out, please, please, please reach out and let's work on it. This is definitely a topic that can kind of get confusing.